The visual universe, including Earth, the Sun, other stars, and galaxies, is made of protons, neutrons, and electrons bundled together into atoms. Perhaps one of the most surprising discoveries of the 20th century was that this ordinary or baryonic matter makes up less than 5% of the mass of the universe. The rest of the universe appears to be made of a mysterious, invisible substance called dark matter and a force that repels gravity known as dark energy. In the earlier 1990s, one thing was fairly certain about the expansion of the universe. It might have enough energy density to stop its expansion and recollapse. It might have so little energy density that it would never stop expanding. But gravity was certain to slow the expansion as time went on. Granted, the slowing had not been observed, but theoretically the universe had to slow. The universe is full of matter and the attractive force of gravity pulls all matter together. Then came 1998 and the Hubble Space Telescope observation of very distant supernova that showed that a long time ago the universe was actually expanding more slowly than it is today. So the expansion of the universe has not been slowing down due to gravity, as everyone thought it has been accelerating. No one expected this, no one knew how to explain it, but something was causing it. Scientists now think that the accelerated expansion of the universe is driven by a kind of repulsive force generated by quantum fluctuation in otherwise empty space. What's more, the force seems to be growing stronger as the universe expands. Theorists still don't know what is it. For a lack of better name, scientists call this mysterious force dark energy. What is dark energy? Dark energy is even more mysterious, and its discovery in the 1990s was a completely shock to scientists. Previously, physicists had assumed that the attractive force of gravity would slow down the expansion of the universe over time, but when two independent teams tried to measure the rate of deceleration, they found that the expansion was actually speeding up. It turns out that roughly 68% of the universe is dark energy. Dark matter makes up 27%. The rest, everything on Earth, everything ever observed, all normal matter adds up to less than 5% of the universe. One explanation for dark energy is that it is a property of space. Albert Einstein was the first person to realize that empty space is not nothing. A space has amazing properties, many of which are just beginning to be understood. The first property that Einstein discovered is that it is possible for more space to come into existence. Einstein's gravity theory that contains a cosmological constant makes a second prediction: empty space can possess its own energy. Because this energy is a property of a space itself, it would not be diluted as a space expands. As more space comes into existence, more of this energy of a space would appear. As a result, this form of energy would cause the universe to expand faster and faster. Another explanation for dark energy is that it is a new kind of dynamical energy fluid or field, something that fills all space, but something whose effect on the expansion of the universe is the opposite of dark matter and normal energy. According to some theorists, dark energy is a fifth and previously unknown type of fundamental force called quintessence. But if quintessence is the answer, we still don't know what it is like, what it interacts with, or why it exists. So the mystery continues. A last possibility is that Einstein's theory of gravity is not correct. That would not only affect the expansion of the universe, but it would also affect the way that normal matter in galaxies and clusters of galaxies behave. This fact provides a way to decide if the solution to the dark energy problem is new gravity theory or not. We could observe how galaxies come together in clusters. But if it does turn out that a new theory of gravity is needed, what kind of theory would it be? How could it correctly describe the motion of the bodies in the solar system, as Einstein's theory is known to do, and still give us the different predictions for the universe that we need? There are candidate theories, but none are compelling, so the mystery continues. What is dark matter? Scientists have not yet observed dark matter directly. It doesn't interact with baryonic matter, and it's completely invisible to light and the other forms of electromagnetic radiation, making the dark matter impossible to detect with current instruments. But scientists are confident it exists because the gravitational effects it appears to have on galaxies and galaxy clusters. First, it is dark, meaning that it is not in the forms of stars and planets that we see. Observations show that there is far too little visual matter in the universe to make up the 27% required by the observation. Second, it is not in the forms of dark clouds of normal matter made up of particles called baryons. We know this because we would be able to detect baryonic clouds by their absorption of radiation passing through them. Third, dark matter is not antimatter because we do not see the unique gamma rays that are produced when antimatter annihilates with matter. Finally, we can rule out large galaxy-sized black holes on the basis of how many gravitational lenses we see. High concentration of matter bend light near them from objects further away, but we do not see enough lensing events to suggest that such object to make up the required 25% dark matter contribution. Scientists have a few ideas for what dark matter might be. One leading hypothesis is that dark matter consists of exotic particles that don't interact with normal matter or light, but that still exert a gravitational pull. However, at this point, there are still few dark matter possibilities that are viable. Baryonic matter could still make up the dark matter if it were all tied up in bone drops or in a small dense chunks of heavy elements. These possibilities are known as massive compact halo objects or MACHO. But the most common view is that dark matter is not baryonic at all, but that it is made up of other more exotic particles like axions or WIMPs, means weakly interacting massive particles. Several scientific groups, including one at CERN's Large Hadron Collider, are currently working to generate dark matter particles for a study in the lab.